We're very happy to continue the seminar this year again. It's my pleasure to introduce Samprit today. He'll be our first speaker for this series, and he'll be speaking about certain polytopes associated to algebraic integer conjugates.
Thank you, Payman, for inviting me to give a talk. And yes, so the title of my talk is certain polytopes associated to algebraic integer conjugates. This is a joint work with Seda, Greg, and Koa. Koa is my postdoctoral mentor here in Calgary. And just to sort of give you an overview, in today's talk, we will mostly be focusing on this object. So suppose you take an algebraic integer alpha of degree d, and let alpha 0, alpha 1 through alpha d minus 1 be its conjugates. And we will label them in a decreasing order of magnitude. So alpha 0 has the largest magnitude and alpha d minus 1 has the smallest. We will investigate all tuples C1, C2, Ck in the first quadrant, or for non-negative values of them, such that this inequality is satisfied. Mod alpha 0 times mod alpha 1 to the C1, alpha k to the Ck is bigger than or equal to 1. Now, of course, we will. I'll first tell you why we care about this, and then what kind of results we can prove, etc.
So, is this for every k less than d or particular k?
That's for no particular k. For any k less than d, we can investigate this. Yeah. Okay. So the motivation comes from a result of Bujo and Wen. So they proved in 2023 the following result. If you have an algebraic number of degree d, let's call it xi, and suppose you have an epsilon, which is greater than 0, and let un be a non-degenerate linear recurrent sequence of integers, which is not a polynomial sequence, then there are only finitely many uns for which xi minus vn over un is strictly less than 1 over un to the 1 plus 1 over d minus 1 plus epsilon. Now, I put this non-degenerate and not a polynomial sequence in quotes because, well, we won't be discussing them today. These are technical terms within the theorem. But let me tell you a little bit of this have some very interesting consequences. One of them is that if you take, let pk over qk be a sequence of convergence to a real algebraic number of degree at least 3, then, and un be a sequence as above, then there are only finitely many pairs for which un can be equal to the denominator of a convergent. Un is equal to qk. Another interesting consequence is that, well, you can kind of use this to improve a theorem of Lenstra and Chalet. They showed that theta is a quadratic irrational if and only if the denominator of the convergence qk satisfies a linear recurrence with complex linear recurrence sequence with a constant complex coefficients. This can be improved to, rather than saying it is itself a linear recurrence relation, to saying that it has infinite intersection with some non-degenerate linear recurrence sequence. So this motivated us to look at, well, one of the questions that the authors, Bujo and Wen, ask in their theorem.
Samprit, could you just go back to the previous slide? So are you saying that your statement about the QK is equivalent to the previous one?
Sorry, which one?
So the Lenstra-Charlotte show that theta is quadratic rational if the QK has a certain property, right? Linear recurrence. And
Yes.
then you're saying you can improve this, which means
Yeah,
that
so that's the theta is quadratic irrational if and only if the sequence QK has an infinite intersection with some non-degenerate sequence.
in other words, that conclusion is equivalent to saying it satisfies a linear recurrence with constant complex coefficients.
Yes, yes.
Mm.
So one of the questions that Bujo and Wynn asked is, can the exponent 1 over d minus 1 be improved at all? So this is sort of where this is the problem that we started with, and then of course, as it often happens with mathematics, you branch out and you look at other things. So to see whether this 1 over d minus 1 can be improved at all, we need to see where that 1 over d minus 1 is coming from. So in their proof, it actually comes from a very simple observation. Namely, suppose fx be a monic polynomial, irreducible, of degree d, and suppose the roots of fx are, again, in a similar fashion, you have alpha 0 through alpha d minus 1 in decreasing order of magnitude. So for any irreducible monic polynomial of degree d, the root satisfies this following condition. Mod alpha 0 times mod alpha 1 to the d minus 1 is bigger than or equal to 1. And this d minus 1 is sort of the source of the d minus 1 in the exponent in their proof. Now, this observation can be, of course, very easily seen. It's just you write alpha 0 to the alpha 1 to the d minus 1. Because we have this decreasing order of magnitude, you replace alpha 1 with alpha 1 to the d minus 2, and then by alpha 2, and so on, all the way up to alpha d minus 1. And so that's precisely f of 0, because we are taking the polynomial in Zx, so that has to be bigger than or equal to 1. So of course, so we can ask then, can we do anything else? Can d minus 1 be replaced with any other non-negative c such that this condition holds? Here is a trivial scenario. It's true for any c between 0 and d minus 1. Why? Because, well, if the second largest root is bigger than or equal to 1, then alpha 0 times alpha 1 to the c is bigger than or equal to 1. If this is strictly less than 1, then alpha 1 to the c is bigger than or equal to alpha 1 to the d minus 1. So alpha 0 times alpha 1 to the c, that's bigger than or equal to 1. Now, in order to see if we can go bigger, essentially, this is sort of what we want. We want to look for polynomials, irreducible ones, which has one very large root. Alpha 0 is very large, and then the rest of d minus 1 roots are very small. And not only small, if let's say alpha 0 is of order h, some h, we will get more into that, what that is, then alpha j, rest of the roots should be of order minus 1 over d minus 1. So are there such polynomials? Yes, we were able to find a family of such polynomials. So here's the family. For any integers d and h, you consider the polynomial x to the d minus hx to the d minus 1 plus 1. Note that for infinitely many h, this polynomial is irreducible in Zx. And this can be seen directly from the Hilbert irreducibility theorem. Now, this polynomial has, the roots of this polynomial has this very interesting property, precisely sort of what we were looking for. If you choose an epsilon, which is between 1 over mod h and 1 minus 1 over mod h, then this FDH polynomial has one root in the annulus, 1 minus epsilon times mod h to 1 plus epsilon times mod h, so order mod h, and rest d minus 1 roots in the annulus, 1 plus epsilon mod h to the minus 1 over d minus 1, and so on. So d minus 1 are very small roots. Now, I will, for the time being, I'll postpone the proof because we will prove a more general version of this proposition. I'll come to it. But for now, let's take it as a fact that this polynomial does in fact have this property.
Right,
Well,
Simply,
yeah.
so in that proposition, are you assuming the polynomial is irreducible or not?
No, so this polynomial, irrespective of irreducibility, it has this property. Yeah, you don't need irreducibility. So suppose this polynomial, then if we apply a 1 alpha 0 alpha 1 to the c, so we can see that the roots from this from where the roots are, from the location of the roots, we can see that then c has to be less than or equal to d minus 1. So to summarize, a real number c bigger than or 0 has the property that every monic irreducible polynomial fx in zx of degree d with roots in descending order of magnitude satisfy this condition if and only if c isn't 0 and d minus 1. So the corollary is the exponent in our motivating theorem is optimal. You cannot do better than d minus 1. We then ask the following questions. We know that it is always bigger than or equal to 1 if you don't consider the trivial case where alpha is a root of unity. Is it always strictly bigger than 1? If so, by how much? Can we write it as 1 plus some term? And then the more interesting question was to consider, if you think of this 0 to d minus 1 as the one-dimensional case, can you generalize it? Or in other words, if we look at all tuples, C1, C2, Ck, that satisfies alpha 0, alpha 1 to the C minus 1 is bigger than or equal to K, what does that look like? And then the third question is, can you then use this more general framework to improve theorems related to those Diophantine approximations? Now, in this paper, we have answered question 1 and 2. Question 3 is a bit more challenging, and question 3 is still sort of a work in progress. Okay, so let's address the second question first. We will consider, we'll call this EKD. It's the set of all tuples C1, C2, Ck, non-negative, such that for every algebraic integer alpha of degree d with its conjugates as alpha 0, alpha 1, alpha k, it satisfies alpha 0, alpha 1 to the C1, and so on, alpha k to the Ck is bigger than or equal to 1. And as before, we are labeling the conjugates in descending order of magnitude. So then we want to ask, what's the shape of EKD? Now here are some pictures. We saw what E1D looks like. It's 0 to d minus 1, that interval. Here's what E2D looks like. So for any d, we're taking k to be 2. E2D looks like this quadrilateral with the. So one thing that I would like you to note is that E1D is contained in E2D. So the 0 d minus 1 is still there. And then there's this point 1 comma d minus 2, and we're joining them in a certain way. Here is a picture for E3D as well. And again, the same observation you can make in the x-axis, the 0 to d minus 1 is there. And then in y-axis, the 0 d minus 2 by 2 comma 0 point is also there. So that entire thing, E2D, is contained in E3D, and so on. So these pictures, by the way, were done in Sage Math. So here's a theorem that we proved, that for d bigger than k positive integers, EKD is in fact a polytope in R to the k with 2 to the k vertices. Moreover, we can explicitly determine what the vertices are. The vertices, and it's given in an interesting way as well. So suppose you take any subset J of 1 to up to k, right? And let's order them. So let's call the elements of J as J1, J2, Jn, where they are in increasing order. J1 is the smallest, Jn being the largest. Then each vertex v1, v2, vk can be written as Vj is 0 if j is not in this set. For the last one, for j equal to jn, it's d minus jn over j1. And for the rest of them, it's jl plus 1 minus jl by j1. So this is what each of these individual vertices look like. Okay, so here's a sketch of the proof. So it turns out that every element or every point in EKD satisfies the following system of linear inequalities. So I'll tell them, I'll tell you what the inequalities are and how to go about them first, and then I'll tell you where they are coming from. So this is the set of inequalities. Of course, the second condition is just coming from that C1, C2, CK being non-negative, but the other inequality is d minus j over j plus the first j minus 1 variables. There's a coefficient d minus j over j minus the next ones minus I equal to j to k xi is bigger than or equal to 0. And again, as we vary j from 1 through k, we get k inequalities in the first one, and then another k inequalities here. So we have a total of 2k inequalities. We figured out how to solve it. Before I guess I have written an example. So E2D in variables x and y will look like that. X plus y is less than or equal to d minus 1. Minus d minus 2 over 2x plus y is less than or equal to d minus 2 over 2. And then x is bigger than 0, y is bigger than 0. So that's what determined that that quadrilateral. So here is how we see that the solution is in fact a polytope with 2 to the k vertices. Now, it turns out that suppose we label or we call this left-hand side as Lj of x, or Lj of x1, x2, xk, right? So for each of the subset I of 1 through k, the linear system Li of x1, x2, xk equal to 0 for I in I. So we are choosing whatever subset I we took of 1 through k. For elements in I, we are taking like those inequalities, and for j that's not in I, we are taking xj equal to 0. So we are taking a bunch of the first inequalities and we are taking a bunch of the second inequalities. And it turns out that no matter what subset I of 1 through k you choose, their intersection is actually there's a unique solution to those. So these are sort of that's how we determine the vertices. You take a bunch of hyperplanes here, and then you take some of the inequalities from here, and their intersection is always a unique point. And so that's what gives us the vertices. And so as you take all subsets of I, all 2 to the k subsets of I, you get 2 to the k vertices. So that's how we determined this polytope. Okay, so where do these inequalities come from? And just like in the d minus 1 case, or the first one-dimensional case, we had x to the d minus h, x to the d minus 1 plus 1. You vary this this exponent as well. So we consider the family of polynomials fdjh, which are x to the d minus h, x to the j plus 1. And again, infinitely many of these polynomials are irreducible from Hilbert irreducibility theorem. Now this polynomial, so this is sort of the general version of the proposition that I stated before and delegated the proof. This polynomial has d minus j large roots and j small roots. Just like the one before, we had one large root and d minus one small roots. It has d minus j roots in the annulus, in mod h to the 1 over d minus j. So that's those exponents are interesting. And then j roots, j small roots. So let's have a look at how we can prove this. The proof is through repeated application of Rouché's theorem. So for example, you take, let's say you take gx to be x to the d minus hx to the j, and lx to be 1, and you take the largest circle. So r equal to 1 plus epsilon mod h to the 1 over d minus j, centered at the origin. So on this circle, we see that gx, which is this, and then you take out the absolute value. And so you get 1 plus epsilon mod h to the j over d minus j, and 1 plus epsilon mod h minus mod h. And so you have this sort of an inequality which is bigger than 1. And again, this last inequality follows from the choice of epsilon. So this is where, from this, we can choose where we want our epsilon to be. And so this means that gx on this circle, gx dominates lx. And so gx plus lx, which is our polynomial, all the roots are inside this circle. Right? That's what Rouché's theorem tells us, that if fx dominates gx, then the inside the region, fx and fx plus gx has the same number of roots. So here, as we can see, gx has d minus j roots, right? It's just 0. X to the, sorry. Yeah, if you take out x to the j, yeah, so it has those roots. Oh, similarly, we can apply. So as I said, it's sort of just repeatedly applying Rouché's theorem. We can apply Rouché's theorem in the smaller circles and figure out how many roots there are inside, and then subtract to say that, well, these many roots are here, that many roots are there. So this sort of gives us the large roots. Right, so here we are taking mod h to the 1 over d minus j, and this is the other one. The smaller roots can be obtained more easily by I guess by a little smarter argument, that you consider the reciprocal polynomial. Once you know where the large roots are, you see that the reciprocal polynomial f star djh of x is just fd comma d minus jh of x. So then you can apply the first part of the result when replacing j by d minus j. And so that's what gives us, that will give you the location of the smaller roots. Okay, so this is very useful, as we will see, to know where these roots are. Okay, so now suppose you take a point C1, C2, Ck in our EKD. That means it satisfies this condition. And suppose among those infinitely many irreducible ones, we pick a monic irreducible FDHX as before. Now, with the information, with the proposition before, with the information of the location of the roots, and choosing epsilon equal to half, so if we take h to be bigger than or equal to 3, we can choose epsilon equal to half. We see that j roots are of size 3 mod h over 2 to the 1 over j, and d minus j roots are of size 2y mod h 1 minus d minus j, 1 over d minus j. And so now if we apply it, plug it back here to the alpha 0, alpha 1 to the C1, and then I guess we are taking logarithm here, we get the following computations. So just taking log in this first equation or first inequality, you get 0 is less than or equal to log of this sum. And then we are using these location of the roots to say that 1 over j plus this plus, and then we are separating this log 3 over 2 and the log and this mod h part. Right? So it gives 1 over j plus I equal to 1 to j minus 1 ci over j times log 3 over 2. Then there are some coefficients of log 2, and then there's a whole bunch of coefficients for log mod h. Now, note that we are saying that this is true for infinitely many values of h, right? For infinitely many values of h, you can find such an irreducible polynomial. And so that means that this coefficient, in order for this entire thing to be positive, this has to be positive, just the coefficient of log mod h. Because these are always fixed. So as you take larger and larger values of h, this really grows. So the coefficient of log mod h has to be positive. So that's what gives you the inequality. 1 plus j plus I equal to 1 to j minus 1 ci by j minus I equal to j to k ci by d minus j is bigger than or equal to 0. So these polynomials are like those, are sitting like, they're like sitting in the boundary. So that's kind of where I think we were pretty lucky to got a hold on these polynomials. Right. So as we vary as we vary j from 1 to k, we see that EKD it has to. So for every C1, C2, CK point in EKD, they has to be contained. They has to satisfy these inequalities. That means whatever our EKD is contained in the solution polytope of obtained from these inequalities. So in order to conclude that EKD is exactly equal to the solution polytope, we just need to prove the other way. So suppose you take a solution of these inequalities, we want to show that that's contained in EKD. Now, by convexity of EKD, it is sufficient to check only for the vertices, that the vertices are inside EKD. And so recall that this is what our vertices look like. So you take any subset of 1 through k, and then for those j's not in the subset, Vj is 0. And for j equal to jn, it's d minus jn over j1. And for the rest of them, it's jl plus 1 minus jl by j1.
Is it obvious that EKD is convex?
Yes. Just from that, yeah, just from here. Yeah, if you take let's see, if you have some lambda 1 c1 is 0.
It looks like it's some hyperplane, right?
Yeah.
Or some half plane defined by a hyperplane. I see. Okay.
Yeah. I don't think it's too much work. I think it might be. Yeah. Yeah. I don't exactly remember. Okay. So now if we look at this alpha 0, alpha 1 to the v1, alpha k to the vk, and just because all these denominators has j1, let's took it to the power of j1. If we do that, what do we get? We get, see, for j not in capital J, the exponents are 0. So the only elements which will appear here are subscript j1, j2 through jn. And then from here, we get that the second coefficient is j2 minus j1, the second exponent, the third exponent is j3 minus j2, and so on. And the last one is d minus jn. And of course, j1, j2, jn are in increasing order like that. So then we just replace this alpha 0 to the bunch of j1s and use that they are in decreasing order of magnitude to fill out the rest. So up until alpha J1, we write it as alpha 0 times alpha 1 all the way up to alpha G1 minus 1. And then you get alpha J1, and then, yeah. And so that just gives you F0, which again is bigger than or equal to 1. So that means, so this side is pretty trivial. Once you figure out those inequalities and what your polytope looks like, yeah, showing that this is in EKD is easy. Okay.
Samprit, you also hinted before that this AKD, for some smaller k are inside of this larger polytope. So this is in general too, yeah.
Yeah. This is in general, generally true as well. And in fact, before, so it took some a good measure of trial and error to actually figure out that these inequalities are the case. Before that was our approach to somehow build EKD from EK minus 1D, because every time we could show that it's actually contained in it, and we are sort of seeing that how to do it, that you're just adding a few more vertex and then creating the polytope. Yeah, but it turned out that this is a much more concrete way of writing things as a solution of these inequalities. Yeah. Okay, so the other question that we are interested in is, when does strict inequality hold, right? Or if the inequality is strict, how big is it? So let's look at the one-dimensional case first. Alpha 0, alpha 1 to the d minus 1, is that strictly bigger than 1? Of course, we're not considering the trivial case where the roots are roots of unity, because then it's exactly equal to 1. So here are some examples, non-trivial examples. If you take fx to be x squared minus x minus 1, the Fibonacci polynomial, then you have then alpha 0, alpha 1, that's just f of 0, that's 1. Right? Because d minus 1 is still just 1. D being 2 here. For cubic polynomials, also you can construct cubic polynomials in a specific way. For example, suppose you take a monic irreducible cubic such that f0 is 1, and 2 of its smaller roots are complex conjugates. Right? So one real root, two complex roots. Then alpha 0, alpha 1 squared, d minus 1 being 3 minus 2. Then you can just write that, because the two conjugates will have equal magnitude. So mod alpha 0 times mod alpha 1 times mod alpha 2. So that's again f of 0, which is equal to 1. So for example, if you want such an example of a cubic, this works. X is cubed plus x squared minus x plus 1. But interestingly, it turns out that if you go, if the degree is bigger than 3, then this is always bigger than 1. So the only examples that we could find were in the quadratic case and in the cubic case. And this, of course, we proved a more general result, which I'll show you next. So here's the result. Suppose k and d be positive integers with d strictly bigger than 3k. Okay, and you take mu to be this integer, d minus 3 minus k over 2. And then we are taking the ceiling functions of that. Let E be the maximum of 2 times d minus 1 times d minus 2, and then d minus 1 times d minus 2 times d minus 3 by 2 mu. Then there exists a positive constant C depending only on d, such that the following holds. For every algebraic integer alpha of degree d that is not a root of unity, and for every C1, C2, Ck in EKD, this is strict inequality, and it's bigger than 1 plus C times h to the minus this E plus some 1 over k over d minus 1. So this little power saving term that we have, 1 over k by d minus 1, these are this is by completely ad hoc methods, which is very specific to this setting that we had. But yeah, this is sort of the main term. h to the minus e. H here, by the way, denotes the height of the minimal polynomial of alpha. And by height, we mean just the maximum of the absolute value of the coefficients. That's what we are using as height. So I won't go, the proof is quite involved, but let me give you some ideas of where we got this from. Firstly, by convexity of EKD, again, it suffices to check strict inequality for the vertices, right? And again, the vertices looks like that. You take a subset of 1 to k, and then you construct the vertices like that. And just like before, if we consider mod alpha 0, mod alpha 1 to the C1, alpha k to the CK, and then you take it to the power I1, then that gives you alpha 0 to the I1, alpha I1 to the I2 minus I1, and so on. Now, in the last situation, we just replaced all of these by the product alpha 0. We saw that this is bigger than or equal to the product from alpha 0 to alpha d minus 1. Here, what we do is we just change this alpha in. So rest of it is as it is. So alpha 0 to the I1 would be bigger than or equal to alpha 0 times alpha 1 times all the way up to alpha I1 minus 1. Then you will have alpha I1 and so on. Rather than this alpha in to the d minus in, writing that explicitly, we replace that by alpha in. We take that twice, and then we only go up to alpha d minus 2. I'll tell you why we are doing it. But I hope this step is clear what we are doing. Rather than going all the way through alpha d minus 1, we go only up to d minus 2, and we take alpha in square. Now, if we do that, then this minus 1, right? So that's what we are interested in, alpha 0, alpha 1 to the CK minus 1. So this particular inequality minus 1 is then you can take out, again, 1 being f of 0, you can take out alpha 0 through alpha d minus 2 and write alpha in minus alpha d minus 1. Now see, this is bigger than just this quantity, right? Because this thing will be just f of 0 over the smallest root, and the smallest root is less than 1. Because if the smallest root itself is bigger than 1, then this becomes trivial. So we are really interested in the case where the smallest root is less than 1. So this sort of boils down to figuring out the separation between the roots, and not just separation, the absolute separation between the roots. So there are a good amount of literature available on that, which deals with separation of roots of polynomials. So for example, the result that we sort of worked with is the following. It's a result of Bujo, Degela, and et al. From 2022, where they show that if you have a polynomial of degree d, any polynomial, and let alpha and beta be two of its roots such that they're not equal. So they're not, their absolute values are not equal. Mod alpha is not equal to mod beta. If both alpha and beta are real, then their absolute value is bigger than h to the minus d minus 1. Again, h being the height of the polynomial. If one of them is real and one of them is not, then the height is bigger than h to the minus 2 times d minus 1, d minus 2. And then if neither of them are real, then this is bigger than this h to the thing, h to the product of d minus 1, d minus 2 times d minus 3 over 2. So of course, if you just apply their theorem directly, then it will tell us that then we would have this as the exponent. In our theorem here, rather than this one, we would just have d minus 1 times d minus 2 times d minus 3 over 2. So rest of however many power savings we got, we we didn't apply their theorem directly, rather we adapted their techniques, and that's how, and modified them accordingly to get that power saving that we are getting. Okay, I think I'm done. So here are some of the references, and thanks if you have any questions.